It's coming from chapter 3. I know that feels awkward, but it is our last section in unit 1. So we'll review and quiz next week, and then we'll review for our tests the following, which will be the beginning of the following week. Okay, but like this is it. Okay. So what we are going to talk about today, and don't write this down, but we're going to talk about limits at infinity. So yesterday we talked about limits, and we described them as infinity or negative infinity. Today we're going to talk about limits towards infinity. The limit as x approaches negative infinity. The limit as x approaches positive infinity. So when I'm asking for an infinite limit, I'm really asking what is the end behavior of the graph. If I'm asking you for the limit as x approaches negative infinity, what happens as you go to the left? What's that end behavior? If I'm asking for the limit as x approaches infinity, what's the end behavior as you go towards the right? Okay. We have a variety of different functions that we know. Okay. We have simple things like polynomials. We have more complicated graphs when we get into the rational family. Okay. So we'll talk about the different strategies that we'll need to take in order to figure out what's happening on the right, what's happening on the left, in the event that we need to evaluate an infinite limit. Okay. So like in the case of this graph, we have a horizontal asymptote here at y equals 3. So you can see as we go to the left, as we go towards negative infinity, our graph approaches 3. As we go towards positive infinity, our graph approaches 3. That's the definition of a horizontal asymptote. Towards the ends, we're going to approach that y value. Trivia. Can we cross a horizontal asymptote?
No. This
What?
discontinuously.
Discontinuously we can? Can we cross a horizontal asymptote?
It's bad. There's got to be a way. We have complex numbers always that don't exist. I think we can do it.
Yes, we can cross a horizontal asymptote as long as it's like somewhere in the middle of our graph, but towards the ends we approach the horizontal asymptote. Those of you who had me or Miss Cronky for a teacher in pre-calculus, you graphed a graph like that. Whether you remember it or not, that's kind of up to you, but we did graph something like that last year. Okay. What? Exciting. It was exciting. It was exciting. Okay, let's start small. Polynomials. We actually are talking about this in pre-calculus right this second. What is the leading coefficient test? Do you remember? It's the test to figure out what's happening at the ends of your graph. So we have, that's even versus odd. We have a rule for if we have an even degree versus an odd degree. If we have an odd degree versus an even degree, it tells us what's happening on the right and left sides of our graph. If the degree is odd, what's true about our left and right side? Okay, they're opposite. Odd, opposite. Even degree, what's true about both sides of a graph? We have the same behavior. Okay. Also in the leading coefficient test, we have to look at the leading coefficient. Okay. If the leading coefficient is positive versus negative, that's going to tell us what's happening on the right side of our graph. Okay? Max, if we have a positive leading coefficient, what's happening on the right side of our graph? Is it going up or down? Okay? If we have a positive leading coefficient, the right is going to rise. If we have a negative leading coefficient, the right is going to fall. Okay? So we can use the leading coefficient test to think about what the end behavior of our polynomials would be in order to determine their infinite limits. Okay? So really, you did this last year in pre-calculus, you just didn't know what a limit was. Okay? But by describing the behavior, you were kind of doing a limit because you wrote infinity and negative infinity in the notation that you used to answer the questions for a leading coefficient test. Okay, so let's look at some polynomials. Okay, really boring and basic stuff. Okay, so 2x to the fifth. We are going to look at the limit as x approaches infinity and the limit as x approaches negative infinity. Okay, so think about 2x to the fifth. Ethan, as we go towards positive and infinity, what's this graph going to do?
It's going to go up.
Okay.
Right.
It's going to rise, so we say that our limit is infinity. Okay? And you knew that because?
It's positive.
Okay, the leading coefficient is positive, so we know, I mean, it's the only coefficient, but the leading coefficient is positive, so we know that towards the right, we're going to rise. Okay? Celine, if we go towards negative infinity, what's going to happen to our graph? Okay, we're going to go towards negative infinity. We have an odd, thank you, an odd degree, so our behavior is going to be opposite. Okay. 5x to the sixth. Think about 5x to the sixth. Alex, what's going to happen towards infinity?
It's going to infinity.
Okay. What about negative infinity?
Infinity.
Okay. We have an even degree, so we know that our right and left hand behavior is going to be the same. And since we have a positive leading coefficient, Alex determined that the right was going to rise. Okay? Go ahead and write down that last set of limits and answer them together with your neighbors. Pierce, what do you got for us? Julia, why negative infinity for both?
Because the degree is even.
The degree is even. Anything else?
And -7.
Okay. Our leading coefficient's negative and our degree is even. Okay, so they're both going to fall. All right. Please do not be tricked. You have these two questions to answer before we move on to our rational graphs. Brinley, what do you have for the first one?
Infinity.
And why do you have infinity?
Because it is positive.
Okay, we have a positive leading coefficient, so the right is going to rise. Our second problem, Trenton, what do you have? And what is your reasoning? I didn't trick Trenton.
Oh, you tricked me. Oh, EB's all alone. Oh, I got tricked. No, I got tricked.
Okay, the highest degree is x to the sixth. So technically your leading coefficient is negative 14. Yes.
I mean, even if you're misreading and use the 17x to the third, you'd still also get negative.
Yeah, you're right. I didn't think about that very well, did I?
I like that.
Okay, be careful. All right. So here we go. So just for simplicity, right, r is positive, and then write this right here. So c is a constant. R is positive. A constant over x to the r. As we go to infinity, it says that limit is 0. Our numerator is staying the same, but what's happening to our denominator? What's happening, Glenn?
Getting infinite smaller. No, well, the denominator is getting infinitely bigger.
Okay, okay.
Overall, it's getting
There we go. So
smaller.
our denominator is getting bigger and bigger and bigger and bigger and bigger, and so our fraction is getting smaller and smaller and smaller and smaller and smaller, and so our limit is 0. Okay. Same thing would happen if we had x is less than 0. So, like our limit, this really, I don't know why this is so fuzzy today. I'm sorry. Same thing if we were to go to negative infinity. Okay. If x is going to be less than 0, then the same thing would happen. If your denominator grows and grows and grows and grows, and your numerator stays the same, then your fraction is going to approach 0. Are we all okay with that rationale?
Yes.
Okay. So then write down this example, please. Sometimes it may be helpful to break up a limit if there's addition and subtraction, and I have no problem with that. Like if you wanted to rewrite this as the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared, that's okay. All right, some of you may not want to do that, but let's just think about it separately, okay? What's the limit as x approaches anything of 5? 5. 5, right? Everything's 5 everywhere. Okay. Minus the limit as x approaches infinity of 2 over x squared. I have a number over x to a power. So as we go to infinity, this numerator staying the same, this denominator is going to grow. So this is going to go to 0. 5 minus 0 is 5. Dylan?
Boys, do we have to split it up?
No, you don't have to split it up.
Okay.
You do not have to split it up. You do not have to split it up.
always watch them.
You're too nice and neat with your.
Yeah. I won't be able to read it if I don't deliberately make it look nice. I won't be able to read it later. I'll rush through it.
Only able to hear my annoying voice.
Okay. Does anybody have an idea of what this would be? Just a guess before we do it. Okay. So if I look at the limit as x approaches infinity of the numerator, that's a line. We'd go towards infinity. If we look at the limit as x approaches infinity of the denominator, that also goes to infinity. This is what we call an indeterminate form. That's, you can't take infinity divided by infinity. That's not okay. All right? So if you have a rational graph, we can divide by the highest degree of the numerator. Okay? And we can't just like divide an entire expression by something. I'm talking about we divide the numerator by something, we divide the denominator by the same thing. So really we're just dividing by 1. Okay? So what's the degree of the denominator? Oh, shoot. No, I am wrong. Please erase that. I got excited. It's the denominator. I'm so sorry. It's the denominator. There's something about the numerator that's exciting, and so we'll see it in a little bit. Okay. The highest degree of the denominator. What's the degree of the denominator? 1. So I'm going to take everything and divide it by x to the first. Nice. This is exciting, right?
Yeah.
The limit as x approaches infinity of 1 over x. The limit as x approaches infinity of 1 over x.
The denominator is going to be bigger, but the fraction is going to be smaller.
So we're going to 0. The limit as x approaches infinity of 1 over x. Woo. And what's 2x over x the same as? What's x over x the same as? What's happening at 2?
It's approaching infinity.
There's a horizontal asymptote at y equals 2. Could we have identified our horizontal asymptote without having to do algebra?
Yes.
How, Pierce?
You take the coefficient of the half x value over the coefficient of
Okay. Your horizontal asymptotes occur if the degree of the numerator is the same as the degree of the denominator, which is what just happened. Then we look at the leading coefficients of both the numerator and denominator. So in this case, it was 2 over 1. So y equals 2 is where our horizontal asymptote was. Okay. What about if the degree of the numerator was smaller than the degree of the denominator? Where's our horizontal asymptote? The degree of the denominator is bigger. Y equals, it's the same number every time, no matter how big. Y equals 0. Thank you, Alex. And then if the numerator has a larger degree, then you have some sort of slant asymptote. And we are not going to be able to give it a numeric value. It's going to be infinity or negative infinity. We'll look at one of those examples. Okay.
So do you want us to write anything down?
Well, technically there's not a horizontal asymptote, so I wouldn't write it under the horizontal asymptote rules, but if you want to make a reminder to yourself that when the degree of the numerator is bigger, then we have a slant asymptote, I'll let that be up to you. Okay. If we have a slant asymptote, we're going to have to use this strategy. Okay? We're going to have to use this strategy if we have a slant asymptote. Okay? But if we know the horizontal asymptotes, that can save us some algebra work and not have to do this strategy right here.
Yeah.
Okay? Brendan, how's it going? Yes.
So we just did a problem where the numerator was larger than the denominator.
No, we just did a problem where the denominator and numerator had the same degree. They were equal. X to the first over X to the first.
Okay.
Okay? All right. So we're going to do this one.
Change your shirt right now.
So
You just they're judging me for it in an offer shirt. She said you got a shirt from and it's not that good.
He also thought I got burgers, right?
I didn't say it like that.
Okay. Isabel, what's true about the degree of the numerator in comparison to the degree of the denominator? They're the same. So we have a horizontal asymptote at y equals 3 over 6.
Oh, what?
I think it's 1/2. Sorry.
Oh.
3 over 6 reduces to 1/2. So if I'm asking you for the limit as x approaches infinity, then we know that our end behavior is going to approach our horizontal asymptote. Boom, no algebra. Write this one down. Heidi, the degree of our numerator is bigger than the degree of our denominator, which means, darn it, we have to do some algebra because there is no horizontal asymptote. So we need to divide by the largest degree of the denominator, x to the first. The limit as x approaches negative infinity of 4 over x. Boom. Goes to 0. The limit as x approaches negative infinity of 5 over x. 0. It's very satisfying. limit those out, right? So what we're left with is the limit as x approaches negative infinity. 2x squared over x would simplify to 2x, divided by, that just simplifies to 1. So if we simplify everything out, we're left with 2x. Well, that's a line with positive slope. What's happening towards negative infinity? We're going towards negative infinity. Okay? When we have a slant asymptote, you will have some sort of infinite answer. Okay? It's just going to happen. This is the last example we're going to do together. This is probably the last one we'll have time for, but I want to at least show you something you're going to see in your homework. Okay. All right, which degree is bigger? The denominator. When we have a rational function whose denominator degree is largest, we have a horizontal asymptote at y equals 0. So towards infinity, we would approach 0, the horizontal asymptote. If I were asking you for the limit as x approaches 1, you better plug in 1. But if I'm asking you for the end behavior, you can think about the horizontal asymptote. Okay? And that's what's going to be tricky next week, is determining what am I looking at. Do I need to find the horizontal asymptote? Do I need to find the vertical asymptote? Can I use direct substitution? That's kind of what we're going to have to sort through. Okay? So here's the deal. You're going to get a problem like this in your homework. Okay? Technically, we can't really say, you're going to have to use that divide by the degree of the denominator strategy. Technically, what's the degree of the denominator?
1/2.
Okay. It would be square root of x squared is x. So you would have to divide up here by x, but then inside the square root, x squared would be in the square root. Does that make sense? Okay. Happy Friday! Enjoy your 3-day weekend! Allie, can I answer a question?
Yeah. So
Okay.
on the score one, well, there was one, like, it was two problems now. When I had a slant asymptote, how do you know whether it's positive or negative?
So when we did the strategy of dividing out the degree,
Yeah.
we could evaluate these limits,
Yeah.
but then when we simplified the algebra, we were left with 2x.
Yeah.
So that's a polynomial where we can use the leading coefficient test to determine what's happening.
Okay. I understand. Okay.
Okay. Thank you for coming today.